What's up, everyone? Sam here from byte.com, and in this video I'm going to show you how to reverse a linked list. This is a super popular interview question for a lot of the top tech companies, and we're going to dig into it right after the intro. And if you haven't yet, make sure that you go ahead and hit that subscribe button and the notification bell to get notified every time we release a new video. All right, in this video, we are going to look at how to reverse a linked list, and specifically how to reverse a singly linked list. So let's talk about this problem, and remember, as always, we're going to break this down and kind of go step by step here. And we're going to look at what is the brute force solution? Well, first we're going to start with what is the function definition? What does this look like? What's the brute force solution? How do we optimize that, etc. So let's dig into this. So first of all, let's define what our function's actually going to look like. In this case, we're going to take in the linked list, and we're actually going to be reversing the list. So what that means is that we know that we're going to take in a node, right? We're going to take in the head of the list, like that. And then the question is, what should we be returning here, right? So in this case, we're actually modifying the list in place. And so you might be thinking immediately, we don't need to return everything. But remember, what does this actually mean? We have, when we pass in the head, it means that we have a pointer. So this is some variable, let's say x, or I guess, this is our head really. So head, which points to 1, which points to 2, which points to 3, which points to 4, which points to null. And now when we reverse the list, what we're going to have is we're going to have head points to 1, and then 1 points to null, and then 2 points to 1, 3 points to 2, and 4 points to 3. And so we have no reference here to the actual head of our list anymore. And so we're never going to be able to access any of this data here. And so what that means is that our return value, what we can sort of figure out from here, is that our return value actually has to be a pointer to this, has to be the pointer to the new head of our list. And so that's going to be our return value here, is also going to be a node. Right? And so we've defined our function here. Now let's talk about how we could actually code this up. And so for starters, I think that one of the things here that we tend to often do is we tend to overcomplicate things a little, especially when we're looking at the brute force solution. Because when we're looking at the brute force solution, we can really make this as dead simple as possible. And so the problem with a linked list, and the reason why this problem's a little challenging, is that we can only reference the data in order, right? We can only reference 1, then 2, then 3, then 4. But there are other data types or other data structures where that's not the case. And so the easiest possible way that we could do this, and do this in a brute force way, is we could copy all the nodes into some other data structure that we could then traverse in reverse order. So for example, let's say that we created an array of objects that are nodes. And so we're going to actually create an array of length 4, and then we would put all these node objects into the array. So we'd have, and I'll call it 1, 2, 3, 4, just to reflect that they're actual node objects here. And then all we could do is we could start at the end, and we could say, okay, well, for 4, I know that I need to take the next pointer, and I need to point it to, I minus 1. Which is 3, so I need to point this here, and then I could come back and I need to point this here, and then I need to point this here, and then when I get to the beginning, I just need to point it to null. So I need to point that to null, and then all I need to do is return this value here, right? Because that would give us the reverse linked list. And so this is not a super efficient solution because we're using extra space here, we're doing some sort of unnecessary work potentially, but this would be a solution that would work, and it would be a fairly straightforward solution that would work. And so the question then becomes, can we optimize this? Can we improve on this? So in terms of the complexity here, we're going to get a time complexity of O of n, right? Because we're basically going to have to iterate through everything once to insert it into this array. We're going to have to allocate the array, and then we're going to have to iterate over the array once. And so everything that we're doing is linear time. And so that's going to give us a time complexity of O of n, and then our space complexity is also going to be O of n, because we are allocating this entire array, right? So O of n here. And so the question becomes, can we do better than this? Right? Like that's really the fundamental question here when we're doing any of these problems is not, can we just optimize for the sake of optimizing? It's, can we do better than what our current best solution is? And so let's think about this for a second. Are we going to be able to do better in time complexity? Well, fundamentally when we think about it, there's not going to be any way to do it in less than O of n time, because minimum we have to update n different pointers, right? We have to go through each node and we have to update the pointers, or the list wouldn't be reversed and we wouldn't be solving the problem. And so that means that we're never going to be able to do better than O of n time for our time complexity here. And now, in terms of the space complexity, we might be able to improve on things, but in terms of the time complexity, we won't be. And so let's look at how could we do this without using extra space? Well, the short answer is that we're going to have to kind of update things as we go along here. And so let's look at how we might do that. So with any of these things, essentially, we know that it's hopefully obvious that we're going to be basically going, at minimum, we're going to be iterating through our list. And so we'll have our list here. And as with linked lists, we're usually going to do a while loop, right? We're basically going to do a while loop that's while the next node is not null or something like that, because we don't have a fixed size or we don't know the size of our list. And so we're going to be going through. And so the way that I like to think about this, and the way that makes this a little bit easier, is let's imagine, since we're doing a while loop, we're basically repeating the same process over and over again, right? We're repeating whatever the contents of that while loop is multiple times. And so let's try and envision this as if we were in the middle of our loop, and how do we basically define what that one update step is, so that we progress one snapshot through our list. And I'll show you what I mean here. So let's imagine that we've started going through our loop, and basically we start reversing the list. So we have something like this, right? We have our one has been reversed and the rest of the list is still in order. And at minimum, we know that we're going to need to have a pointer here and a pointer here, because otherwise we wouldn't have reference to all of the data. Right? And so the question becomes, how do we move from this to here? Oops. Basically, how do we move from this to the next stage of our loop? So now we're going to have pointers here and here. And what you can see is we basically, we're in exactly the same state. And so, except just moved one step through our process, right? And so what are all of the things that we need to do to get from state one to state two? And if we can do this, this is just the body of our while loop. And so this is how, when we break down the problem this way, it becomes a lot easier for us to see what we need to do. So how are we going to get from step one to step two? Well, we know that we're going to need to create a pointer here. We know that we're going to need to do this, update the pointer, right? And so we know that one of our steps is going to be, let's say we have a current, let's call this previous and this current, so that we have some nomenclature here. We're going to say, okay, so we know that previous, we know that current.next equals previous, and that's this step. That's this step right here. But when we did this, okay, crap, now we lost our pointer to 3. And so what we know that we need to do is, before we do that, let's actually make sure that we save that pointer somewhere. And so I'm going to go ahead and say, before we do this step, let me create a next pointer, so that I have a reference to the 3. And so that means I'm just going to say that, next equals current.next. Right? So I did this first, and now when I update the pointer here, I'm not losing that data. And now you can see that these two look almost the same, except the pointers are not in the same spot. And so we need to update the pointer. So how do we get from 1 to 2? Well, we're going to say, okay, previous equals current, right? Because that's going to move previous to here. And finally, current equals next. So we have current here. And then it doesn't actually matter what next is, because next is not relevant in this, since we're setting a brand new value every time for next. That's, defined within the loop. But when we have this is basically our entire while loop. Just these 4 steps. And so we're basically going to loop through this, and then all we need to do is figure out what is going to be the condition where this while loop terminates. And so, if we extrapolate this, our end state should be 1, 2, 3, 4, and then if we look at it like we had here, that basically means that this is previous, and next is going to be what was here, which is null. So null. Or, sorry, this should actually be current is null, right? So current is equal to null. And so that gives us our while loop, right? We can just say while cur is not equal to null. And so this way, by basically stepping through this, we've defined a solution. And I'm not going to go through the whole code, but this is, we would just do this loop for the list, and then we would return, and then we see that, previous is the actual value that we wanted to return here. So we would finally, return previous. And so this is how we can do this in an iterative way. This is going to take no extra space, right? Because all we're doing is we have these 3 pointers, but that's a fixed amount of extra space. And then we're not doing anything else. And so that's how we could do this iteratively, and how we could do it in linear time and constant space. And now I quickly also want to go through how we could do this recursively, because that was one of the questions in the Leetcode version of this problem. So I want to make sure that we are on the same page with this, but we have to realize that this is not actually going to be as efficient of a solution, because the problem with recursion is that we always are going to be storing all of the stack data. And so that means that our space complexity for doing this recursively is actually going to be O of n, and so it's a less efficient solution. But let's look at how we would do this notwithstanding. And so the easiest way, I think, to think about this is, we can think about this in terms of subproblems, right? So we're going to be recursively saying, f of 1, which then calls f of 2, which then calls f of 3, which then calls f of 4, which then calls f of null. Right, this is the basic structure that we're going to have when we do it recursively. And each of these, what does this function actually mean? Well, f of the node means is a function that reverses the list from that node to the end of the list, right? And so what this should return just null. This should return 4. This should return 3, 4. This should return 2, 3, 4, and this should return the whole thing reversed, right? And actually, really, it should return the whole thing pointing to null. So that's the, basically what we are going to look at here is we just need to figure out how to connect all these together. And so the easiest solution here, honestly, is that we can just update the, if we pass in the previous value, we can just basically reverse the nodes. And so my function can just say, essentially, if, if n is null, or head is null, I guess, let's call it head, then we're going to return. But otherwise, let's basically, what we can do is we can say, we can take in our head into our function, our head and also our previous. And so if head is not null, then we can just say head dot next equals previous. And so the way that this is going to work, if we actually walk through this, is, okay, let's go to the end of our list here, and let me erase some of this so that it's a little bit easier to see what's going on, because we also need to pass in the previous value here, right? I'll just rewrite this. So for our beginning, we're going to say f of head, which is going to be 1, and then we're going to pass in the previous node, which in this case, just by default, our previous is going to be null. And that makes sense because at the end of the day, we want that final node, we want that what used to be the head to point to null at the end. So essentially what you're saying here, another way to look at this is, what should this particular node be pointing to at the end of the day, right? And so then we're going to call f of 2 and 1, we'll call f of 3 and 2, we'll call f of 4 and 3, and then we'll call f of null and 4. And so what's going to happen here is that f of null and 4, think about, remember, we're going to have our whole list, and we're just passing the references. So we have our list 1, 2, 3, 4, null, and we also have this kind of imaginary null over here as well, although there's nothing pointing to it. And so here, we do nothing, we just skip it, and we return back, and now we're going to say in this, head.next, so 4.next points to 3. So we're going to remove this, and we have 4 points to 3. Now we return back up, we're going to have 3 points to 2. So we add that, let me fix this, 3 points to 2. Then we come back up to here, we say 2 points to 1. And then finally, we come back to this top level and we say 1 points to null. And what we might want to do as well, and what might make this easy, is we could also return a node here. So we could just say, you know, if, and honestly, like, we don't really need this step, right? Because we don't need to come all the way down to here. So we could just say, for example, instead of having this here, we could say if or actually, so what we could do is we could rewrite this a little bit. We can say head.next equals previous. And then we could say if head.next equals null, we're going to basically return head, because that's the final value, return head. And so what this is going to do is we're basically returning the new head of our list, right? So if it's the final element, we return head, and otherwise, we are going to make our recursive call, right? And so we can return, in this case, f of head and head.next. And so when we do it this way, it kind of goes in the opposite order from what I described right here. But just to quickly walk through this, again, I want to make sure that we're just like all on the same page here. So we're going to call f of 1 and null. So we have 2, 3, 4. We're gonna, and we need to save our next. So we'll say next equals head.next. And so I'll say, okay, so next equals 2. Then I'm going to update this pointer. So now this is going to point to null. Head.next now points to previous, so null. And then here, you know, we should have our, instead of using head.next, we're going to use next and next. And so what this means is that we're going to say, okay, head.next it points to previous. Now, if next is equal to null, which it's not, we're going to come down here. We're going to say f of head, which is 1. Or I guess we're actually, this is backwards because we're doing head first and then previous. So it should be next head. So we're going to do 2, 1. And now we're going to do the same thing. So next is going to be equal to 3. We're going to come in here. We're going to say head.next is equal to previous. So we update this pointer here. We're going to say return f of next and head. So f of 3, 2. We do the same thing again. You can also see here how I'm like walking through the code, because this is absolutely like the way that you want to do this in your interview. So we're going to point it here. Next is equal to 4. We go through one more time. We have f of 4, 3. We're going to we're going to say next equals null. And so here we hit this base case. So we're going to say next equals null. We're going to do head points to the previous. So we're going to point this here. And then if next equals null, we return head. And so we're going to return the 4 back. So basically what happens is we return the 4 back, and then it propagates all the way up to the top. And so we ultimately return 4. And that's how this works in this case, where we have that additional logic of actually returning our head all the way back up to the top. And you don't have to do it this way. You could do it as an extra variable somewhere. There are a lot of ways you could approach it, but I think this is sort of the cleanest way to do it. And so that's 2 different ways that you can reverse a linked list. Thanks so much for sticking with me through this video. If you enjoyed this and are looking for more, you can check out our free 50 interview questions guide, where we go through 50 of the most common coding interview questions. And if you like this video, make sure that you hit that subscribe button and the like button. Let us know what you thought, and check out some of our other videos. We have a ton of other content like this, and I look forward to seeing you in the next video.